Hello and welcome to Vodcast 16.2. In this podcast, I will explain how we classify stars using HR diagrams. Hertzsprung-Russell diagrams are very helpful tools when it comes to star classification. They show the relationship between stellar brightness and temperature. And when we reference stellar brightness, we're talking about absolute magnitude or luminosity. To gain a conceptual understanding of absolute magnitude, imagine lining up all the stars in the universe in a circle around you so that they're all the exact same distance away from you. As you turn in a circle to look at all the stars, you'll notice that some are brighter than others. And although I know this sounds strange, when scientists compare the absolute magnitude of stars, the more negative the number, the brighter the star is. The more positive the number, the dimmer the star is. As an example, our sun has an absolute magnitude of positive 5. And when you look at the sun's position on this graph, and reference the absolute magnitude, which is shown vertically on the right-hand side of this graph, you see that in terms of stellar brightness, our sun is a very average star. But if you take a look at Betelgeuse, which is a star I referenced in our previous podcast, it has an absolute magnitude of negative 5.5. If you put Betelgeuse right next to our sun side by side, so that they were the same distance away from you, Betelgeuse would look blindingly bright compared to our sun. Now, another very important concept shown on these Hertzsprung-Russell diagrams is surface temperature. That little blurb you see in red is extremely important to note. The color of a star indicates the surface temperature of the star. Your blue stars will have much higher surface temperatures than your yellow and red stars. So put as simply as possible, if we divide this diagram up into vertical columns, the stars that you see in the left-hand column will have the highest surface temperatures, and these stars will typically appear blue. Stars with lower surface temperatures will occur more towards the right side of this image. Red stars will have the lowest surface temperatures, and the orangish and yellowish stars will have higher surface temperatures than red stars, but much lower surface temperature than blue stars. So keep in mind that when we reference Hertzsprung-Russell diagrams, the horizontal axis represents surface temperature. The highest surface temperatures will be towards the left side of the diagram, and the lowest surface temperatures will be to the right side of the diagram. The vertical axis of a Hertzsprung-Russell diagram will always represent stellar brightness. So just as an example, Proxima Centauri is located towards the bottom right portion of this diagram, and what that basically tells us is that Proxima Centauri is a dim star, and it also has a low surface temperature. However, if you look at Betelgeuse, it's located towards the top right portion of this diagram. With an absolute magnitude of about negative 5, Betelgeuse is a very bright star, but it has a relatively low surface temperature. And just an FYI, red giants and red supergiants will usually have low surface temperatures. One final example is the star Spica. Spica is located in the top left portion of this diagram. When considering stellar brightness, this star is pretty bright. It has a luminosity just under 10,000, and its absolute magnitude is fairly close to negative 5. And because this star is located to the far left side of this diagram, it has an extremely high surface temperature. In fact, if we extrapolate down to the horizontal axis, the surface temperature of this star is probably over 25,000 Kelvin. The final consideration in this vodcast are the types of stars, and these are evident in the Hertzsprung-Russell diagram. The first star type that we'll consider are main sequence stars. 90% of all stars fit this classification. The main sequence stars are found on the band that runs through the center of this Hertzsprung-Russell diagram. So any stars you see on or very close to this line represented here are going to be main sequence stars. Our very own sun is a great example of a main sequence star. And to understand what a main sequence star is, it's a star right in the middle of its lifetime. These stars can be thought of as stable and happy. The next type of stars that we'll consider are the giants, or more specifically the red giants. Giants are large and very luminous. You'll find these stars in the upper right portion of the Hertzsprung-Russell diagram, and these stars are typically going to be in the later stages of their lives. I've noticed that as I've reached the later stages of my life, I've started to bloat a little bit. Well, these stars do the same thing for different reasons, because I don't think they're eating chicken wings. But as I'll discuss in a future podcast, the giant stars are nearing the ends of their lives. The giant stars will die relatively quiet deaths, but the supergiant stars will go out in a blaze of glory. In fact, it's these very large supergiant stars that go supernova. and when they do, they end up forming either neutron stars or black holes. Now, keep in mind that the overwhelming majority of stars are going to be main sequence stars. Only a few percent of the stars out there now are either giants or supergiants. The final star type that we'll consider in this podcast are white dwarfs. In fact, the ultimate fate of our Sun is to become a white dwarf. The white dwarfs are much fainter than main sequence stars. And if you look towards the bottom portion of this diagram, you'll see all the white dwarfs. All of your white dwarfs will have low luminosities and low absolute magnitudes. These stars are also small, many of which have sizes comparable to planet Earth. Not all white dwarfs will be white, and as you can see in this image, some are blue and some are yellow. But it's important to note that, very roughly speaking, white dwarfs are the remains of dead stars. And in the vodcast to come, when I discuss stellar evolution, we'll see that white dwarfs are the end stages for low mass and medium mass stars. Okay, that concludes this video podcast. In our next vodcast, we will take a detailed look at stellar evolution.